Hi, welcome back to AP Physics C, Unit 3. In this video, we're going to look at the work energy theorem. In the last video, we talked about work and kinetic energy, but now we're going to combine them into this single theorem called the work energy theorem. So the way we think about it is that the net work done in a system is the work done by all the forces that are acting on the particle. So just like when we wanted to find net force, we would just do, to find network, we would do W1 plus W2 plus W3 plus ... depending on how many forces we have acting. So what this actually means is that the forces are going to affect the motion of the object. Well, when we have forces, or when we have specifically a net force, we tend to accelerate the object. But when we accelerate, we change the velocity of the object. So what does that mean? If the motion of the object is affected by the forces, then the kinetic energy will change, right? Because we will have a change in velocity, which will affect our kinetic energy. So the way we think about it is that the net work done on a particle equals the change in the particle's kinetic energy, and this is what we know as the work energy theorem. Or mathematically, what we say is the net work is equal to the change in kinetic energy. Now, again, this is probably what was talked about in the Physics 1 course, but understand that the network is really specifically change in any energy. So it can be mechanical energy, it could be potential energy, right? Or it can be kinetic energy, where mechanical energy, remember, is K plus U, right? The kinetic plus potential. But remember, because we have calculus involved, it could be simply that F dot dx, right, is equal to 1/2 mv squared minus 1/2 mv initial squared. Or because of the calculus, we can have it set equal to that integral, not work. Sorry. This would be force. So force dot dx is equal to 1/2 mv squared minus 1/2 mv initial squared. And I forgot to point out in the last video, because we have an integral, work is the area under a force versus displacement graph, okay? And that may show up on a free response question or even a multiple choice question. Okay, so let's look at an example problem. So here we have a bullet mass 40 grains or 2.60 grams with a muzzle velocity of 335 meters per second. It can penetrate 8 1-inch pine boards, each of a thickness of 0.75 inches or 1.79 centimeters. What is the average stopping force exerted by the wood as shown in the figure? Okay. Oh, sorry. And so what we have here is we have to do some converting. So the mass of the bullet, 2.60 grams, which is 2.60 times 10 to the negative 3 kilograms, because remember, we always want to be in kilograms. The next part we have to convert is the distance it travels. Well, it's going to be 8 times 1.9 times 10 to the negative 2 meters, right? Because that's that in centimeters, right? 1.9 centimeters is this, which is going to be 0.152 meters. Okay, and I'm looking for F. So we're going to start with our work energy theorem. So the net force is equal to F, or sorry, not F, but 1/2 mv squared, or the change in kinetic energy. I jumped the gun a little bit, and we're going to roll with it. So this is F delta x is equal to 1/2 mv squared minus 1/2 mv initial squared. So all I have to do now is divide all this by delta x, and I get an equation. I'll clean it up here to look like m v squared minus v initial squared divided by 2 delta x. In fact, the equation v squared equals vo squared plus 2a delta x comes from this kind of relationship, because remember, F equals ma. So if I plug in ma there, I actually end up with this cake formula. So now I can plug in my numbers. Oh, I can do a simple canceling here. We're coming to a stop. And so really it's going to be F equals negative mv0 squared over 2 delta x. So F is going to be negative mass 2.60 times 10 to the negative 3 times v0 squared, so 335 squared over 2 times 0.152 meters. And I'm going to get an answer so we get a average stopping force of negative 960 newtons. Right? If we wanted to find the acceleration, all we do is F that number over m. That will give us the acceleration, which would be quite big because of the fact that it's a small object, right, experiencing almost 1,000 newtons worth of force. All right, so in the next video, we're going to look at power because it does, again, it just kind of rolls into the alignment or it is what's affected by the other two. And so after that, then we'll talk about potential energy, conservative forces, non-conservative forces, and conservation of energy.